Today we're going to talk about superconducting qubits and quantum computing. So this is Adrian, my colleague. So in this talk, we'll talk about four sections. The first thing is classical and quantum computing, like the comparison of them, like what kind of difference can they provide, and then what can quantum computer bring to us, and then how do we build a computer? Like it's very advantageous. And then how do we build a quantum computer with superconducting qubits? So we will. So first, so for classical computing, actually the first generation of computers start from vacuum tubes in 1939, and the vacuum tube actually is quite slow and weak, and it can generate a lot of heat like light bulbs. And by the early 1960s, actually someone invents transistor, so it's much lighter and also smaller, and then it's more efficient and require less energy. As you can see, as time passes, we have more and more transistor inside one single. So then the question would be, how can we increase this the number of transistor infinitely in a chip? So actually, someone answer the question. So before answering this question, let's take a look at how transistor look like. Okay, so anyway, so the transistor actually is made of three parts. So it has source part, drain part, and also the gate part. So gate part can control the current between source and drain. Then and more, this guy, he predict that the number of transistors doubles every 18 months. So you can see at this figure shown. So the x-axis is the year production year, and the y-axis is the number of resistors that number of transistors that we use. So you can see that it's approximately 2 years we double the transistors in a chip. And one thing to note down is that so the distance of so how small it is defined by the you can roughly think that it's defined by the distance between source and drain. So as it increases so as the transistor gets smaller, actually there's a problem that we will face. So because now the source and drain they're getting closer and closer, so electron has less distance to travel. So it's possible that we cannot block the flow between them. Then it will introduce the effect that we call tunneling. And this tunneling will cause us that the transistor is not transistor anymore. It's not like we want to turn on and turn on, we want to turn off and turn on. It will become maybe it has some tunneling between each other. So it will be problematic. So the solution, there are two kinds of solutions. One thing is we try to make the transistor maybe don't have this kind of quantum effects happen, or we can also embrace quantum mechanics. So we can try to build quantum computer using a quantum. So actually in classical, we have it can be separated into information processing, extracts information. So information we have bits. So it's either 0 or 1. There's never have so you cannot have superposition of 0 and 1. And when we process, we can have a Boolean logic, which is where we input 0, then let's say now the gate is not. So we input 0, then we get 1. If we input 1, then we get 0. And after the information is done, after the processing, then we want to extract the information. Then the information that we get actually deterministic. It will be either 0 or 1. And for qubit, actually they are very different. So for qubit, actually it can have different probability superposition of 0 and 1. And alpha and beta is the probability of alpha and 1. And then it also have the unitary operation that so psi actually is the initial state. And after applying some unitary operation, like the supernova, we can also apply the C naught, the NOT gate. Then after that, it can be 0 can goes to 1 and 1 can goes to 0. And however, one different thing is that, so you can see, so let's say now we measure. So based on the probability difference, we will have alpha 0 squared will go to 0, and alpha 1 squared will go to 1. So for example, now we have 1,000 times our measuring. So let's say this is 0.3 and this 0.7. So you have 30% times that you will measure 0 and 70% times that you will measure 1. So actually, everything is deterministic, but for extract information, actually, it's probabilistic. So what can quantum computer do for us? So actually, one application, one motivation of building a quantum computer is that it can break the RSA encryption. So RSA is basically the three people's name. So I will briefly illustrate how RSA works, but it will have more illustration in your future class. So first it will have Alice. And so real now Alice wants to say, okay, nice to meet you. And he wants to send to Bob secretly because she didn't want anyone to know. And then so now you can encode with some key. And then after that you can get something that it doesn't make any sense. So no one will know if you don't have the key. Then after that you transfer to Bob and Bob can decode. So Bob only get a ciphertext. Then after that, Bob can use the key to decode. Then Bob can receive, oh, it's nice to meet you. So maybe Alice has some feeling with me. So for this, because they are doing secretly. So okay, so the total process of RSA is not too simple. It's actually it need the safety is built on top of a big number. So actually to generate a key, actually Bob need to have 2 prime numbers. So it has, and then others need to encrypt the message, but it's okay, you don't need to know the detail. And then eventually Bob can decode information and get the information. So the only important thing is that is safe. This classical cryptography is safe because it's built on top of it's very difficult for classical computer to factorize the products of 2 very large prime numbers. Okay. So actually, there's a very smart guy who's called Shor, and Peter Shor said that there's a quantum algorithm that it can very fast, like faster than the quantum, faster than the classical computer, and it can break this RSA. So maybe in a few days or so. So actually, we can make more. So if you are more interested in more algorithms, you can check this quantum algorithm zoo. So here I just provide one example on how quantum computer can work. Then okay, the question would be how do we build a quantum computer if this is advantageous? So there's another guy called dimensional criteria. So he proposed that so there are several criteria to fit in order to build a good quantum computer. And the first thing is qubit. So you need to have a well-defined 2-level system that it represents 0 and 1. So for example, let's say now you have a multi-level system. And in order to be a good qubit, you need to make sure that it's confined into these 2 levels. So it doesn't jump up. Because if it jump up, then it's not qubit anymore. And also we want to initialize our qubits at the ground state so that you don't have let's say it's like when you open a computer, you don't want it to jump any place that you don't want it to go. Only if when you do operations, then you go to the upper level. And then so this initialize the qubit. And of course, so let's say now I open a PC and now I'm doing some calculations. And if now PC suddenly shut down and nothing's safe, and I don't want that to happen. So usually we want the long coherence times, so that is longer than our gate operation. So within the gate, before all of my gates finish, then it didn't decay. And then, so in order to implement any quantum algorithm, actually we need to have universal gates sets. So which means that you can do all the control that you want to implement different kind of state. But sometimes it's not too trivial. It's not like, okay, I want a NOT gate and I want NOT gate, or I want an OR gate and I want an O gate. It will be like more complicated depending on what your goal is. And also, of course, we want to measure the qubit so that we can extract the information on what kind of result that. And so in terms of, so now let's say we have one chip and now we have another chip. So in order to have like long range communication, and we would like to have something called flying qubits so that it can communicate with long distance. So one example of the qubits in optics, as you just learned from the previous lecture, is that you can have in different direction in the electric field. So you can represent like horizontal and vertical, and then horizontal can be represented as 0, and vertical can be represented as 1. However, there's a problem of this is that it's harder to engineer. So let's say I want a certain frequency, or I want how much coupling between each qubit, or so it depends on how much engineerability that you want. So optics is a bit harder for that. So superconducting qubit actually is a very good platform that you have a different building block. So this is capacitor, inductor, and this junction. Also, my colleague will introduce more in experiment side later. So you can think about it just a Lego. So based on this Lego set, you can build your ideal set of the circuit that you want. So you can have a different, so you can attain different goal.
Let's take a step back and also refresh a bit of what you guys learned yesterday. So let's talk about a bit of superconductivity more specifically. If you remember Alex's presentation yesterday, everything starts in 1911 in Leiden, Netherlands. Was Hamerling ons the used liquid helium and so on. He's doing some measurements. He takes some mercury filament, and then he's passing a current through the filament, and he's measuring the voltage drop, so he can calculate the resistance. And then he thinks like, oh, what happens if I cool it down? Like I know how to prepare liquid nitrogen, liquid helium. What happens when I cool it down? Everybody expected that everybody knew that the resistance of metals decreases as the temperature decreases. But then what he observed is that it decreases until a certain point where it suddenly drops to 0. And it doesn't drop like, oh, it's just very small. It's 0, at least up to the measurement precision that we have nowadays. We just measure absolute 0 resistance. So it was not until 1957 that John Bardeen, Leon Cooper, and Robert Schrieffer come up with some theory that we now call VCS theory that explains why this is happening. So this theory basically it says like when we have a metal, we have our positive ions, and then the electrons keep like bouncing, or as we say scattering on the ions. So this scattering, they are constantly hitting each other, hitting the ions and so on. And this produces some temperature, some heat that, for instance, is how light bulbs work. But then if we take this and then we cool it down below a certain critical temperature, from now on TC, for instance, the critical temperature of aluminum is around 1 Kelvin. then the electrons actually bound into what we call Cooper pairs, and these Cooper pairs completely ignore the ionic structure. And to have a bit more insight of how these Cooper pairs are formed, we can have, so here I have some illustration. Here we have a very well-defined array of ions. Then when an electron passes through, here the important thing to notice is that the ions are way more massive than electrons. So electrons are very, very fast in comparison to ions. So first you have your electron that passes by, and then after a certain time, the ions slowly start to react to the charge of the electron. So there is a certain delay between the electron passing and the ions actually moving. So we actually have here, we will have this electron will be gone, but we still have a certain concentration of positive charge. So if there is another electron passing by, it will feel attracted by this positive charge. So in some sense, these two electrons are kind of bound together and they form what is called Cooper pair. So there is some kind of like, it's not entanglement, but there's some kind of interaction between the two electrons that for the experts, and they need opposite spin, so they become the bosons. So what does this mean? When we have a normal metal with a temperature above the critical temperature, everything is as we know, electrons are just bouncing around. But as soon as we cool it down, then all electrons couple, like form Cooper pairs. They interact pairwise and they form Cooper pairs. And these Cooper pairs don't have to be like the two electrons don't have to be like physically close together. They can be like distant apart, but they still interact. It's still a pairwise interaction. So one of the most surprising things is that once our material becomes fully superconductor, we the superconductor has a wave function that is macroscopic. Like this is one of the few times we can see quantum mechanics with our bare eyes because it's up, you can have superconductors as big as you want. It's like a macroscopic object behaves as a wave function. And so to give some intuition why you can explain superconductivity with quantum mechanics is because, as I mentioned before, superconductivity measures zero resistance. There is no dissipation. And in quantum mechanics, if probably you learned yesterday in your tutorial, all the evolutions are unitary, which means you can evolve and evolve back. There is no loss in quantum mechanics. So it kind of makes sense like, oh, if I don't have any loss in my piece of metal, maybe it's because I can explain it with quantum mechanics. So you may be used to use like wave functions that when you integrate the wave function across all space, across all universe, it's normalized to one, which means like, for instance, if I take the wave function of one particle of one electron, the wave function squared is the probability to find the electron in a certain position. So when I integrate over the whole universe, of course, the probability is one, it will be somewhere. But now what, at least in superconductivity, what we use is we model this superconductor with a wave function for the whole superconductor. So to sense like all the Cooper pairs like behave in the same like we call it coherently. They behave along the same way. All of them move together. So everything just a giant wave function. So when we integrate this wave function squared, what we find is like the integral gives the number of Cooper pairs in the superconductor, which is nothing more than, of course, the number of electrons over two. Two electrons form one Cooper pair. So we have, now we can find, oh, what's this wave function? We know that when we square it, it has to be not square, but when we take the absolute value square, it has to be the number of Cooper pairs. So we kind of know like, okay, it must be something that goes like a square root number of Cooper pairs. And then since usually wave functions are complex numbers, we just give here some degree of freedom. You say that the superconductor has some phase. So this is the wave function of a superconductor. So what are the properties of superconductors? One, we mentioned already, they have zero resistance. So we can have a current without any voltage drop. The second property, which is kind of fundamental as well, is that when we have a normal metal, so the temperature is above the temperature, we can have put a magnet nearby, and then our magnet generates a magnetic field, here represented with these vertical lines. But once I cool it down, once this metal becomes a superconductor, it actually repels the magnetic lines. This is called Meissner effect or perfect diamagnetism. But basically what you need to remember is that the magnetic field cannot penetrate into superconductors. It doesn't exist inside the superconductor. And there is yet another fundamental property, which is even more weird, which is called flux quantization. And how is it? I just mentioned that there cannot be magnetic field on the interior of the superconductor. But what about if my superconductor is like a donut? So magnetic field, once it's in its metal, magnetic field can penetrate through. Now I cool it down. Okay, the magnetic field that was inside, it's expelled. But what happened with the field in the hole of the superconductor? And then it turns out that, and this is related to the phase that I was talking before, the amount of magnetic flux, which is the magnetic field times the area that is in the hole of the superconductor, has to be a multiple of what we call flux quanta. Actually, just define like h to e. So this allows us to see quantization with our bare eyes. And if we try to change we for instance put a second magnet below the superconductor such that we increase the magnetic field lines, our superconductor itself will generate a current to oppose this change because the field inside can only be 150, 250, 350, but it cannot be 1.150. So if I try to put 1.150, it will generate a current that fully compensates for this 0.1. So it's only 150. And this is what we call persistent current because if I now turn off my magnetic field completely, it still cannot change. The field inside cannot change, right? So the superconductor will take care to generate a current that keeps one flux quanta on the interior. So the superconductor itself became like somehow like a magnet now. And then this current will flow forever, or at least it has been when they started doing these experiments, like, I don't know, 30 years ago, the current is still there. So persistent is like a good name. So these are the three main effects. And now what I want to mention, which is related to the demonstration we will just perform, is that there are two kinds of superconductor. So if you also remember Alex's presentation yesterday, he was saying that when we have a magnet and we pass particles, like when a particle flies over the magnet, depending on its spin, it deviates up or down. So this kind of gives you an intuition that if our magnetic field is very, very strong, it will break apart the Cooper pairs. So then the superconductor won't be a superconductor anymore because all the Cooper pairs are broken. So this is what happens. If we have, if our temperature is below the critical temperature, temperature is just, probably you learn in school, is just the average kinetic energy of the particles. So if our temperature is very high, because of thermal excitations, the Cooper pair break apart. But also if the field, if the magnetic field is very high, the Cooper pairs are ugly. And of course, they can work together if temperature is a bit high. So we also have quite a bit of magnetic field, and both of them will work together to break up the Cooper pairs. This transition between normal metal and superconductor. Type 1 superconductors are like more usually like single elements like aluminum, niobio, mercury, tantalum. And they are very well explained by the VCS theory. But there is another kind, which very originally we call it type 2 superconductors, where when you start applying some magnetic field, or the Cooper pairs are fully broken, they will let some of the magnetic field penetrate into the superconductor. So this is what we call like a flux vortex. The superconductor locally, like in a small region here in orange, will become a normal metal. And then one flux quantum will pierce through. So then we have a superconductor, like it's fully superconducting. After a certain field, we will have a mixture of normal areas and superconducting areas. And if we keep increasing the field, of course, at some point, everything will be just a normal metal. So these type of superconductors are a bit nicer because the critical fields are higher, so they can withstand more field. We can create more powerful magnets with them. They have higher critical temperatures. You don't have to cool it down to like 1 Kelvin. You can have them at 70 Kelvin. But they are usually more complicated. They are more complicated crystals, and they are not very well explained by the VCS theory. So now that we know that we can actually, once I put my superconductor on top of a magnet, if the magnet is strong enough, it will it will let one flux quanta pierce through. There is a new effect that we call flux spinning, so to say. So if we have an array of magnets and we put a superconductor on top of it, we will generate this vortex around it, actually like thousands or millions of these vortices. And these vortices take energy to move. So like we would only create vortices when you apply some force with your hand or whatever over the magnet, over the superconductor, sorry. And once they are inside, once the superconductor is fully pinned, it stays in place because moving the vortices around or disappear of the vortices like disappearing would take energy. So the superconductor would rather not do that. And this is what allows actually magnetic levitation, which can be used for these trains and so on. So we can do the demonstration now. So this is just, okay, this is kind of simulating. This is kind of simulating like a magnetic levitation train where you would have the rail here. These are just magnets. And that used to be a type 2 superconductor. Yeah, let's put it so big. So if once here we have some just liquid nitrogen. So I'm using a type 2 superconductor also because the critical temperature is bigger than the liquid nitrogen temperature. So when we place it down, if it works, it should just levitate. And of course, like it will be able to move with almost zero resistance. So This is like fishing. Okay, here it is. So I place it here, then I would pin it, and then it's fully pinned. Like it can move around, and it fully levitate. And okay, we lost our superconductor. This is a borrow superconductor, and which is not very strong. Technically, if I would just place it like on a higher position, like every time I apply some force against the magnets, I'm pinning more or less flux quanta. I'm pinning more or less flux quanta, so it will stay in place. If I push it closer to the magnets, it will stay closer to the magnets. Like this. Temperature. So now let's see if it works. There is like flux spinning doesn't matter if the rail, if this magnet is on top or below, or if the superconductor is on top or below the magnets. So we should be able to do the same experiment with the rail upside down. Let's try. Maybe upside. Okay. Let's start here. It takes a while to cool down. That's why sometimes it doesn't fully work. And also, like at some point, like we were playing so much yesterday that it felt so many times. Well, it's like dust, the superconductor, but okay. Okay, we can try it. See. Yeah, like that. Okay, well, let's try and we continue with the presentation.
It's supposed to look like.
So before we have the bigger one, the bigger one actually you can do like this and then go down.
Just wow. So we can wrap up the superconductivity part after this experiment. So let's now enter in like, okay, how do we build a qubit out of superconductors? Or why are we using superconductors at all? So the most basic element you can build out of a superconductor is just a quantum harmonic oscillator. So it's basically, you have to imagine it's just a yellow thin strip of like metal. You know, in our lab we use aluminum. So this yellow strip is just okay, this is like maybe like 10 centimeters long, but like a few millimeters wide. And it's just some aluminum that we deposit on top of this bluish thingy that is a sapphire crystal. And then when we go to the lab, we can show all of this. And then we place this line into a also aluminum like panel and everything. Then we cool everything down until it becomes a superconductor. So we have here two different things. Alan, are you guys familiar with capacitors and inductors? Oh yeah. Okay. Good. So it's a very thin strip of metal. So we can imagine it's like a wire that we are passing a current through. So it will have some magnetic field. So it has some inductance. And at the same time, uh, you can imagine this is just a 3D version of a capacitor. Like this would be one plate of the capacitor, and all the tunnel, the walls of the tunnel is like the other bit of the capacitor. So you can have like an electric field and so on. So you also have some capacitance, which we can model like that. The quantum harmonic oscillator is just some inductor and some capacitor. And once you use quantum mechanics, you find that this actually has energy levels that are evenly spaced, where the energy difference between two levels that we call h bar omega r is just given by 1 over the square root of the inductance and the capacitance. And it's an harmonic oscillator because like an analogy of this would be like when you have like a string attached on both ends, and then you play like you like string your string, and then it starts with oscillating, and it can oscillate with different modes. It's the same, but instead of like having a string that physically oscillates, what we have here is we have some current or some electric and magnetic field that constantly oscillate back and forth. So it has some oscillation frequency, which is exactly this frequency. So this is nice. We can fabricate this, cool it down, but we cannot use it as a qubit because it has infinite energy levels, but all of them are separated by the same frequency. So this contradicts what Nini just explained, that we need two well-defined energy levels. This is not a qubit. Brian Josephson in the 90s, he came up with this with the Josephson junction. So imagine we have a superconductor, then we grow a certain oxide barrier in between, and then we place another superconductor. They have some phase, so they can actually tunnel through the junction. So if we plot, for instance, the current versus voltage for a normal metal, we have what you may have studied, of course, Ohm's law. So voltage is just is linearly dependent on the current, and the dependence is the resistance. So if we plot them, okay, voltage versus current, we have just a straight line, and the slope of this line, in this case, it would be 1 over r. But if we take this Josephson junction and we plot I versus V, what we find is this, which is basically governed by Josephson equation. So this is like a very rich, like there are a lot of things happening here. But two things worth noticing is like even when you don't have when the voltage is 0, you still measure some current. And this is just the Cooper pairs tunneling through back and forth. So this is purely quantum mechanically. No voltage, nothing applied. You just have the junction there, and then you measure some current. And then you can see that if your voltage is actually very, very strong, it kind of like looks like it has like this linear relation. So it kind of looks like a normal metal again. And it's indeed because if the voltage is very strong, it turns like a normal metal. You just break superconductivity. You're breaking the Coulomb pairs again. And in between, there are like all sorts of things happening, which are given by this equation. And the only thing I want you guys to remember is that, for instance, here we are seeing that when we have a voltage, the phase of our superconductor will change in time. And then we have a current that depends on the sign of the phase. So they are not linear anymore. This is highly non-linear, which is exactly what we want. Because if we take our harmonic oscillator, but instead of the inductor, we replace the inductor by a Josephson junction. Here we represent as a box with a cross. So it looks like this. We have certain capacitance because this is just a capacitor, but we just place it on the plane. But there is an electric field between both parts of the capacitor. And in the middle, we have a junction. So our junction has a certain energy that you can just trust me is flux quanta squared over a certain inductance. Then what happens is that now our energy levels have different energy splittings, that they have different transition energy. So now we can define a qubit. This is just like having the hydrogen atom. People that use like ions for quantum computing. Of course, ions have like many energy levels. What you want is just to have two energy levels that have a very specific frequency, and then there are no other energy levels at this frequency, which is exactly what you will have. And we can engineer in the lab this frequency by changing these energies, which basically means like you can make the junction bigger or thicker, or you can make your capacitor paths wider or longer, and then you will be able to engineer whatever you want. And that's why some people call these transform qubits, people call it giant atoms. Because what we are doing is like we are engineering atoms, or at least their transition energies in the lab at will. So that's why superconducting qubits is one of the most promising platforms for you, because you are not just limited to what nature gives you, so to say. It's not, oh, I can only use like calcium ions or beryllium ions, like people that use ion traps, but you can design your own atoms. So the qubit, if we zoom in, the junction looks like this. I think the junction was fabricated by Nini. So this wire, and okay, this scale, this is 1 micrometer. So these are very small junctions. This wire would be like this wire over here. And then this is the other one. And in the middle, if you can see, there is some overlap between both of them. So they are overlapping here. And in between this overlap, yellow thing is the oxide barrier. So we deposit the aluminum. This is sapphire, this is aluminum deposited. Then we grow some oxide, and then we deposit the second layer of aluminum. And in the middle, we have the junction. So this is a real qubit we use. And this is I think Alex was telling you about scanning electron microscope and so on yesterday. This is taken with a scanning electron microscope. So you're, of course, this is too small to see in a normal, with a normal microscope. So you basically shoot electrons and then you measure the electrons back just because they have a smaller wave function. But there is some problem of using superconductors. Is like, of course, you need, I mentioned at the beginning of the presentation that the transition energy of aluminum was 1 Kelvin. So we need to be able to cool down to 1 Kelvin. But there is even more, which is that having a certain temperature will excite our qubit. So if our qubit is in a ground state, but we have a certain temperature, it will be in the excited state. So that would not be usable. And to calculate what temperature is good to have, what temperature we can operate our qubits at, we can check some equations. So if you are not familiar with Boltzmann constant, this is a Boltzmann of statistical mechanics that Alex was talking about. The Boltzmann constant here, KBT, measures, this is the average energy due to temperature. So you want that the average energy of the qubit is way smaller than the transition energy. So the qubit won't be excited because of temperature. If you plug some numbers, we have a temperature way smaller than 0.2 Kelvin, which is not easy to get. So we can visualize this temperature of like, we know that liquid nitrogen liquefies at 77 Kelvin. So we cannot use just liquid nitrogen. Liquid helium, hydrogen, sorry, at 20 Kelvin. Liquid helium at 4.2 Kelvin. This is what Kamerlingh Onnes was using when in his experiments. Still too hot. We have to cool down at least below 1.2 and ideally way below 0.2 Kelvin. And we are almost touching the absolute zero. So if you work the math carefully, you need a temperature that is at least, that is around 10, 20 millikelvin. So if you want to visualize, this means we need to operate qubits here, right? Like 10 millikelvin above the absolute zero. And luckily, we have developed what we call dilution refrigerators. Later we will show them in the lab that can actually go down to 7 millikelvin. So of course, the colder you are, the better. The less probability your qubit will be excited. So this is how the dilution refrigerator works. Is quite interesting, but it's also quite hard to explain. But let's see. Do you guys know what are the three ways of heat transport? Yeah. Okay. Conduction, convection, and radiation. So, this is how the dilution refrigerator looks like. Why does it look like this? Okay, first of all, we have here different stages that when you cool it down, it will be cold to like different temperatures. So these pillars that sustain the different stages are isolating, so you don't have conduction. Then you will pump all this volume to vacuum, so you won't have any convection. So the only thing we need to care about is radiation, because all the lab, basically everything, it has a certain temperature, so it radiates infrared and different frequencies. And that's why we have several stages, because we will use different like shields to protect. So this plate is at room temperature, and then it will get into this plate, but then this plate will like absorb and attenuate part of this radiation, and then it will only radiate a bit less, and then this plate will radiate a bit less, a bit less, a bit less, and our superconductor will be placed in here at the very bottom of it. So only this part is at 10 millikelvin. This is like 1 Kelvin, 50 Kelvin. You have what we call mixing chamber. So the way the dilution refrigerator works is by using a mixture of helium-3 and helium-4. The normal helium, the one you know is helium-4, which is a boson because it has 4 protons, 2 neutrons, 2 electrons. But from like basically nuclear power plants, you can extract from nuclear reactions, you can extract helium-3. It has 2 protons, 1 neutron. That's why it's called helium-3, and it acts as a fermion. So if we like take a cross cut of this part, what we have here is we have in this cylinder like a bath of helium-4 that it sits at the bottom because it's a boson, but it sits at the bottom, and then this tube is this has a middle tube here that you cannot see, but on the inside it has yet a smaller tube. And what you can do here is you can pump helium-3 through it. So then helium-3 is kind of like it diffuses. Okay, that's not intuitive, but you're pumping helium-3 into helium-4. whatever that means. And it kind of like dissolves into helium-4. And when it diffuses, you know that when a gas diffuses, increases the volume, it lowers the temperature. So this is what's happening. You are pumping helium-3, it's diffusing, and then it lowers the volume. And then you collect it back and you repeat the cycle again. And then this lets you cool down technically absolute zero. But of course, you will always have a bit of radiation, a bit of conduction, and so on. So it's never absolute zero. It's like 7, 8 millikelvin. So disclaimer, when we go to the lab, you won't see this. You will see when it's fully closed. So it looks a bit more free. So finally, okay, now we have our qubit, it works. It has two well-defined energy levels. It's cold enough. How do we control the qubit? As I mentioned, the qubit, we engineered it to be in the gigahertz regime, which is right in the microwave range. So we need to be able to send microwave pulses. So as a comparison, for people that use ions and atoms, they use lasers. Then these lasers travel through optical fibers. Yesterday you were talking about total internal reflection and so on. And then this excites the electrons in the atoms. So analogously, we use a microwave generator that generates like waves that travel through coaxial cables, and then we send them to qubit. So, and these waves, of course, has a certain amplitude, certain frequency, but like we know when we take an atom like calcium, we know what's the transition frequency because it's in the books. Like we have been using calcium for like centuries, so or tens of years, so we know the exact frequencies. But what's the exact transition frequency of the qubit we just fabricated? So to do that, we do what is called qubit spectroscopy. So we take our microwave source, we take our qubit that if we don't do anything, it stays in ground state. And then what we will do now is we will send different pulses, different microwave pulses at different frequencies. And here we will observe the power that is transmitted as a function of the frequency we send. So if our frequency is very, very high, we won't see, like it will just ignore the qubit, and then we will measure full transmission. If our frequency is very small, the qubit will stay in ground state. We will still, all we are sending is transmitted, so we will measure all the pulse. But when we send a pulse at the exact transition frequency of this qubit, then the qubit will absorb, become excited, and then we won't see anything because all the power is being absorbed by the qubit. And then you will measure a dip in your transmission. So if you do this for like 100 frequencies, you will have this kind of like spectroscopy. Well, this shape is actually a Lorentzian, but basically this allows you to measure what's the frequency of your qubits. So now we know the frequency of our qubits. So how do we control the superpositions of G and E? What we do is we send different different pulses at that specific frequency, but at different amplitudes, which is or different powers. Amplitude and powers are related. So if I send a very small power, my qubit will barely move. It's mainly in the ground state. If I increase the power a bit of the amplitude, then my qubit starts to pass in the Bloch sphere. Being here, it means that 50% of the time you will be in ground state and 50% of the time you will be in excited state, which means that you are in a superposition of both. And when you send a pulse at the proper frequency, at the proper frequency, yes, but at the proper amplitude, you will fully excite your qubit. So you will measure for excited state. And that's how you operate with qubits. So now I ask you, what happens? I send even more power. Does anybody know if I send a wave even more strong? So if I when I pass a very small amplitude, it's a bit excited, then a bit more, it's half excited, then a bit more amplitude is fully excited. So if I keep increasing my amplitude, if you remember yesterday's lecture, there is something called stimulated emission. So when I send even more amplitude, the excitation of my qubit just goes away with the photon. They go, both of them, the photon I'm sending and the excitation of the qubit, they go away. So my qubit returns to the ground state. So, and last slide, so we can have any proportion of G and E. Last slide is like, okay, if I send this like cosine wave, I'm flipping around this axis. So I end up in a superposition of 0 plus of G plus E. Anybody knows what happens when instead of a cosine, I send a sine wave? Anybody has any guess?
Let's go back. Wait, no.
They're like same amplitude, same frequency, same everything.
Wait, what does flip around y-axis mean? It goes the other side of the y-axis.
I see like what's the direction?
Oh,
That would be, I would send like the inverted one, like a minus cosine, then it would flip the opposite direction. But that's correct. Like if I use a sine, what happens is that it flips around the other axis. So now instead of here, I have it here. So, and that was the last ingredient we needed. Because now I can not only prepare any superposition of G plus E, but I can go anywhere in the log sphere. So I have what we call universal control. I can go to any point by log sphere.
Okay, folks, so the second part of the lecture is a lab tour.